In this video, we are going to do some practice problems to review the DI method for integration by parts. So what is the DI method? So let's say we have a integration by parts problem. So like for fx integral of fx gx dx. So the first step is we can use the acronym LIAT. So we know that. So LIAT for to pick. So what we normally call the rule to pick a u. Let tell you which one we're going to pick as u in the integration by parts formula. So this is the priority order. So what is light means? Light means L for log, I for inverse trig, A for algebraic, T for trigonometric, and E for exponential. So you can see the log is the very first one. So if you see log term, we're going to pick that one as L as the U term. And then if you have the exponential term, we're going to pick that one as the last term. We are not going to pick that one as U, because the reason is when you take the derivative, it doesn't make it simplify. So the idea is for the U function, the first function, we're going to pick something that is easy to take the derivative. That's the D1. For the second one, we're going to pick something easy to take the integral, that is the I term. So the first one we take something that's easy to differentiate. The second one we're going to pick something easy to integrate. And then we make this table. So this is called like a DI table. So what we do, we put the fx function on this side, whatever that you pick as u term, and the other one is a v term. And then we put the I, that's the whatever we pick as the I term or the v term. Now what we do, we take the derivative of the first term. We can write as f1 x, and then we take the integral of the second term. We can write this one as g negative 1 for the integral, and then keep going. So take the second derivative and then take the second integral, negative 2. So keep going. So that's the idea until we get the you can stop any moment, but if you get a 0, you are lucky, because then you get like a nice answer. And this is the nth derivative, this is the nth integral. We don't know whether any of them are 0. And then what we do that we're going to multiply them one step down diagonally. So just go one step down and then multiply diagonally, and then keep going. So you're going to multiply these two, and we're going to multiply this with the one over there, and we're going to multiply bottom one with the one above, like that. And then we multiply these two also. So, and then there's a sign convention. The first one we put a plus sign, then the minus sign, then a plus sign. You switch the sign all the way. And then so last one is, so you can see there are n many derivatives, so it is negative 1 to the nth power. So the previous one should be negative 1 to the n minus 1 power. So that is the Liat formula or the argument. So this is how we do it. So let's look at this idea in a problem, and things should be very easy if the last term is 0. Sometimes what happen when you take the derivative, you might see this term is 0, but that doesn't happen always, but it will happen. So we can do problems of both types to see what's gonna happen. I mean, what happened whether like is 0 or not. So let's look at some examples now. So let's do the first one. So as the first one, we can do x cosine x dx. So we're gonna recall some of the formulas. So we know the integral of sine kx dx, k is a constant. It is simply negative 1 over k cosine kx plus c. If we have the cosine kx dx, which is 1 over k sine kx plus c. So now let's try to form the DI table, and then clearly you can see there's a polynomial here. So, and then we have a trigonometric function there. So according to Liat, you can see according to Liat, what will happen? So it is so you can see algebra term comes before the trigonometric term. So that means we're gonna pick, so it's a DI. So we're gonna pick x term as the u term, and the cosine x term as the v term. So that means, So u terms comes first. So we can write x on this side, cosine x on the other side. Now what we do? We take the integral, we take the derivative, and we take the integral. The integral of cosine is sine. So it is sine x. And then again, take the derivative, and then take the integral. So it's a sine, so it's negative cosine. Since we get a 0, we're going to stop. Now what we do? We're going to multiply across the diagonal, start with a plus sign, and then minus sign. So we're done. Now we can write the answer. So that means our integral is, so it is x cosine x dx equals to, if you multiply the first diagonal, you're going to see x sine x. And then if you multiply the second diagonal, there are two negative signs, so it becomes positive, and then you get cosine x, and then plus c. So that's the answer. So you can see it's like a really neat and very short method. So you can do problems really quickly using this argument. So let's look at the second one. For these kind of complicated ones, this DI method helps you really well, because you can see if you try to use the other technique, it's really long. But you can see like this is very beneficial like for problems like this. And we need a new formula. So we have this exponential function. That means we know this one. The integral of e to the kx, k is a constant, is simply 1 over k e to the kx plus c. For this one, k has to be a constant. So let's make the table, and it's very clear what is the and then again according to a Layat. So you can see we have algebraic expression and we have exponential one. So algebraic one we're gonna pick as u, or the differentiate one. So this the one we're gonna take the derivative, the d term, and this one we can pick as the I term. So let's make the table now, d and I. So we have x3 minus 2x plus 3 e to the negative 2x. So we take the derivative first. So it is 3x squared minus 2. If you take the integral, you have to divide by negative 2. That means multiply by 1/2. So negative 2x. And take the derivative. So it is 6x minus 0. We don't write it. And divide by negative 1/2 means multiply by negative another 1/2. So that means 1 over 4 e to the negative 2x. And then take the derivative, which is going to be 6. And when you multiply by negative 2 again, so it's negative 1 over 8 e to the negative 2x. It doesn't look like 8. And then 6 means 0. So this is negative, this will be positive 1/16 e to the negative 2x. So that's what you get. And then again, we're going to multiply across the diagonal. So we're going to multiply these two with the plus sign, these two with the minus sign, these two with the plus sign, and then the last two with the minus sign. So that's what happened. And then we can write the answer now. So the integral, which is x3 minus 2x plus 3 e to the negative 2x dx. So we can write this one as the first multiplication is 1/2 x3 minus 2x plus 3 e to the negative 2x. That's the first one. Second one, you get a minus, again minus 1/4. So you get 3x squared minus 2 e to the negative 2x. And the next one is again minus. So you see minus. If you multiply the numbers, you get negative 1 over 8. I just write what we get. So the 6x e to the negative 2x. And the last term is again minus. It's kind of interesting what happened here. All of them are minus. You get 6 over, I didn't simplify here, I just write it like that. 6 over 16 e to the negative 2x, and then add a c here. So that is the answer. I mean, for these kind of things, especially in exam, we are not going to simplify this. We can leave it like that. But for homework, we are going to simplify this one. So for in exam, you can just leave it like that. So because it's going to take so much time if you want to simplify. The best way to simplify something like this is take this one as a common factor. So once you take this one as a common factor, it's not that difficult to simplify. You take this one as a common factor and also take the common denominator. Once you do that, in this case 16, you see that it's very easy to simplify. So that's the kind of idea. but I'm not going to simplify this one for the moment because it's going to take too much time. Okay, so let's look at the next one, and also it's very clear like how fast we can solve the problem. So let's go to the next one. So as the next example, we have x tan inverse x secant x dx. So again, we have a trigonometric and algebraic. So this is the d term, and this is the I term. First one is easy to take the derivative, second one is easy to integrate. So that's the idea. So we can write the di. So d is x, I is tan x, secant x. So we take the derivative, which is 1. Take the derivative, take the integral of tan x secant x. We know that the tan x secant is the derivative of secant. So that means if you take the integral, you end up with secant, because tan x secant is the derivative of the secant. Now take the derivative on this side, take the integral. We know the integral of secant is kind of strange, is the natural log of secant x plus tan x. So if you do not know this, and you need to study the common integral table, and I have given the link in the description for the common table. That's something you need to remember. Okay, since we get a 0, we can stop. So that means we're going to multiply these two with the plus sign, we're going to multiply those with the minus sign. So we can write the final answer like this. So this is equals to x secant x, and then a minus natural log tan x plus secant x. So that is the answer for this problem. So let's look at the next one. This example is a very special, and you will see why is that. Because you can see there are no polynomials here. That means even when you take derivatives or integrals, is never end, because exponential function never end when you take derivatives, and trigonometric function also never end when you take derivatives. So that means this is going in a different route. So, and then also for this problem, it doesn't really matter which one we're going to pick as u and the v. So for this one, I'm going to pick this one as the u term or the d term, and then this one as the v term. So we're going to make the di table. So let's see what happened. So it's a d and I. So we're going to put the e to the negative 2t as the d term, and actually here I did not follow the light rule for this one, because you can see if we put the light rule, then it will be other way around, but we just go with like that. Now we take the derivative of the first term, which is negative 2 e to the negative 2t. We take the integral of the cosine, which is sine 3t, and also 1/3. So there's a 1/3 in front. 1/3 sine 3t. Now we take the derivative again, so which is 4e negative 2t. On the other side is negative 1/9 cosine 3t. So, and you can see you can keep going, but there's no point. The reason is, when we know that the last step going to give you the integral, the first going to give you the result. So for example, so when you multiply like this, so it's a plus sign, this is a plus, and this is a minus, and then so you can stop at any step. So in this case we can stop, and that's going to give you the integral. So but this is a plus sign, because this is plus minus plus. So what happened here is, now you can write the answer like this. So the answer is, as we did before, we do the same thing. So it's an integral e to the negative 2t. Actually what I'm going to do, just to save some space, then I can put all of them in one screen. So let's try the answer here. So this equals to, if you multiply the first diagonal, you get 1/3 e to the negative 2t sine 3t. That's what you get from the first one. And the second one, you get there are 3 negative signs. That means negative 2/9 e to the negative 2t cosine 3t. That's what you get from the second diagonal. The third one is not a diagonal, so it's an integral, and again it's going to be minus. So it's a minus 1/9. I write number outside. We have the integral e to the negative 2t cosine 3t. So that means if you multiply across the, if it's diagonal, you get the term. If it is horizontal, you get the integral. So remember that. So you get the integral from the last one because it's not diagonal, it's horizontal. Now what you'd notice is you get the same thing that you start with. That means we can do some algebra. What's the algebra we're going to do? We're going to move this term to the others. Actually, there was a 4. There was a 4 on the top. So there's a 4 here. Yeah, we're going to move this term to the other side. So that is the algebra how we do. We're going to move because it's the same term. So if you move that to the other side, or that means if you add that term to the other side, then you can get double of that. Double means like you can simplify that. So that means you're going to get 1 plus 4 over 9, the integral, e to the negative 2. So this is a very nice trick. Cosine 3t dt. The other side actually we get a number. So you can see just 1/3. You can pull them out. Actually, you can pull. Let's say the common denominator. Common denominator is 9, and you can also see that negative e to the 2t is common. So you can pull it out and let the common denominator. Once you do that, you're gonna see you get 3 sine 3t and then minus 2 cosine 3t. That's what you get. We are not going to add the c yet. Now what we do, we can simplify the left side. If you simplify left side, you get 13 over 9. So you can see 9 get cancelled. So you divide by 13. That means your answer is e to the negative 2t cosine 3t dt equal 1 over 13. That's what you get here. And then e to the negative 2t. So you're going to get 3 sine 3t minus 2 cosine 3t plus c. So that's the answer. So you can see it's a really nice argument and should be very useful for a problem like this. Otherwise, it will be very difficult math if you want to use the standard argument for this one. Okay, so let's do one last problem. And again, like another one, maybe using a log one. Because we didn't do a log one here. So let's do a log one. Let's say we have square root of ln x dx. Remember, ln x is different when you see according to Lyot. If you see a log term, we're going to take that one as the derivative term. So that means we're going to switch the terms and then square root x dx. So what we're going to do is we're going to use this one as the d term, this one as the I term in the table according to Lyot. So let's write the answer now. So we're going to make the table. So it's a d and I. D is the natural log term and the I is the square root term. Take the derivative of the first one, which is the derivative of natural log is 1 over x, that we know. And integral of the second one is 1/2 power, that means x going to be 3/2. And then you divide by that, means you flip over and write it like that. So that's what you get. And you can see again that when you take derivatives, it never end. If it never end, we can stop early. So we're going to multiply these two diagonal. And then we're going to multiply this along the horizontal with the minus sign. So what does that mean? Now you're going to get square root x ln x dx, which is equals to the first two terms going to give you the answer, part of the answer, ln x, and then minus the second part going to give the integral, which is 2/3 the integral of 1 over x times, you just multiply the terms, x to the 3/2 dx. So what we did, we multiply the two terms. We just multiply these two. That's how we did. So and then we can simplify this a little bit. So you see this is 2/3 x 3/2 ln x minus 2/3 the integral of, you can see one of the x get cancelled, so you can cancel this and you get 1/2. You can subtract 1. So it is x to the 1/2 dx. Now it's very easy to integrate. So if you integrate this one, you can see it is 2/3 x 3/2 ln x minus, when you integrate, you get another term, is getting 4 over 9 x to the 3/2 plus c. Now you can see, I mean you don't have to, but you can simplify this one because you see this term is common. So we again take the common denominator. So we can write this one as x to the cube square root divided by 9, and then you're going to get 6 ln x minus 4. You can see this is much better than the previous one. So that is the answer for the problem. This is how you solve problems in DI method.